Hello, my name's Darren Holmes, and today we're going to be doing some physical computing programming. We're going to be hooking up some LEDs and some switches to our Raspberry Pi Pico. So to start, we're just going to simply use the onboard LED that's included on our Raspberry Pi Pico. So if you've seen my Chapter 3 video, you'll notice I showed you the schematic for the Raspberry Pi Pico, and on there was an LED. The LED is connected to a general purpose I/O pin 25. Pin number 25 is not brought out to our I/O pins on our Raspberry Pi Pico. It's actually on the Pico board itself. So in order for our programs to talk to the pins on our Raspberry Pi Pico, we need to install a library. This one's going to be called Machine. So it says here the Machine library exposes what is known as an Application Programming Interface, or API. You may have seen this on your laptop computer somewhere. What this does is it allows us to set up a variable. In this case, the variable is going to be called LED underscore onboard, and it's going to be equal to Machine, which is the library that we've just installed. We're going to go to pin and 25, and we're going to set pin 25 as an output. So machine.pin.out. There's a whole series of libraries available for MicroPython, so I want to show you some documentation. So if you go to your favorite web browser and type in MicroPython, you can see that there is an actual micropython.org. So clicking on that link brings us to the MicroPython web page. From here, we want to click on Docs, and you can see we get an overview of MicroPython documentation. And in here we have library references, and we're going to click on the quick reference for RP2. So RP2 is our Raspberry Pi Pico, and you can see we have a quick reference here. You can scroll down. Tells you all kinds of information. Tells you a little bit about the machine module. So you can see we can import machine. We can change the machine's frequency. There's a time module. And in machine, there are the pins class. So I'm just going to come over here and click on MicroPython libraries. And in here it tells you all about the libraries that are available to you. You'll notice there's one for OS, time, Bluetooth, machine. As you can see, there are Python standard libraries and micro libraries. There's MicroPython specific libraries, which include the Bluetooth and the machine that we're going to start using today. So beside where it says machine, it says functions related to the hardware. Go ahead and click on that link, and you can see it brings up machine functions related to the hardware. So as you scroll down here, you can see there's all kinds of different related functions. There's one for frequency. And then at the bottom here, we have classes associated with machine. So we have classes pins, so go ahead and click on that link. So in the pin classes, it's for controlling the I/O pins. You can see we can actually import part of the machine library. So here we're importing pin from the machine library, and we don't have to call it machine.pin every time we go to use it. So there's a lot of information in here. I don't expect you to be able to read it all at once, but as you need things, you can come here and reference this section. And down here on the left-hand side, you can see we have versions and downloads. So you can click on latest. And then in here, we can see we can go to downloads, PDF, and just click on that. And it will bring up the document, MicroPython Documentation Release 1.18. So you can just come over here to this little file folder and do a download. Make sure Save File is selected and click on OK. And we'll save that to our Downloads directory. So in this talking point, you can see we have selective imports. So it's possible to import part of a library rather than the whole library. So there is from machine import pin. So for today, we're just going to import machine, and then in our variable LED on board, we're going to say it's equal to machine dot pin, and we're going to be using pin 25 because on our schematic it's GPIO pin 25, and we're going to go machine dot pin dot out to set up this pin as an output. So while we've set the pin as an output, we now have to give it a value. So LED onboard dot value is equal to 1. This will turn our LED on. And LED underscore onboard dot value 0 should turn our LED off. Because our microcontroller, the Raspberry Pi Pico, operates so quickly, we're going to import UTime. We've used UTime before, so we're going to import UTime to give us a delay between turning the light on and off. In this case, we're going to use utime.sleep5 to give us a 5-second delay. So our final code is going to look like this. We're going to import the machine. We're going to import utime. So those two libraries will be imported. Then to the variable LED underscore onboard, we're going to assign it pin 25 as an output. Because we want this to be a continuous loop, we're going to use the while true. So the LED is going to be assigned a value of 1, turning it on. We're going to wait 5 seconds. We're going to turn the LED off. We're going to wait 5 seconds and come back up to the while true and turn the LED on. Wait 5 seconds, turn the LED off, wait 5 seconds, and then continue our loop. So I've opened up Thonny and I've typed in the code exactly as it's shown in the book. Just a couple things to note is the P is capitalized on pin and out are all in caps. So I've called this blinkled.py. So I'm going to go ahead and run it and show it to you on the actual Pico. So now we should come back and press the stop button to stop our program from running on the Pico. And now we can change some of these values here. So let's go ahead and look at utime sleep 5. Let's change that to 1. Now let's run this and see what it looks like on our Pico. So let's stop our program from running. If you want it to run even faster, you can use decimals. So I can use 0.25. So it only goes to sleep for 1/4 of a second. So let's run that on our Pico and see what it looks like. So there's a few things in the code that I want to mention. We used the variable LED underscore onboard. You could have used any name you liked here. You could have just called it LEDO, so you didn't have to type in the entire onboard. So I'm going to go ahead here and show you what that looks like. It's just so you can type less code in. So I'm going to go ahead and run that. and you can see the program runs the same as before. Now there's a couple things to mention here. When we use the variable name LED or onboard and we assign it to a library that's machine, the textbook tells us it's actually using the machine library's API. And what that means is this becomes a little more than just a variable. It's now referred to as an object. And because it's an object, we want to try and change the value of the object. We have to use the dot value instead of equal. If we were to try and go ahead here and say something like this, it will not work in our code. So this will not work in our code. Because this is an object, we have to use the method. So the method is dot value. So you notice I can change it back by just doing a copy and paste and change that back to 1. So our variable becomes an object, and to assign a value to an object we have to use the method dot value. So as we're reading through the textbook, you'll notice at the bottom of page 48 it says there's another way to handle the same job, and that's by using toggle rather than setting the LED's output to 0 or 1. So what we're going to do in our code is we're going to say while true LED onboard dot toggle. So we're using the dot toggle method for the object LED underscore onboard. So I'm going to show you what that looks like in the code. So I've entered the code into Thonny, and you can see we only now have 2 lines of code instead of 4. So what's going to happen is whatever the value was of that LED, it's now going to be toggled to the other value. So if it was on, it's now going to be off. If it was off, it's now going to be on. So we're going to wait a second, come back, do our loop again, and toggle it to the opposite. So if it was on, it's now going to be off, and if it was off, it's now going to be on. So I'll show you what that looks like. So let's stop our code. Now we use the toggle method, so I just want to show you the documentation again. So in the MicroPython docs that we just downloaded, there's our LED.toggle, and it tells us it toggles the LED between on and off. But you notice there's also other methods in here. Be interesting to play with intensity, but you notice there's also LED off with no value in it, and LED on with no value in it. So in Thonny, I've come along and I've tried to use the method .on with no value in the brackets and .off without any value in the brackets. So let's go ahead and try that and see what it looks like. So I'm going to come back and stop my code from running. So you can see not only do we have commands in the book, but we also have commands in the documents that we can try out. So this is why I try and show you additional documentation that you might not have thought to go and check, because sometimes when you look at code on the internet, you'll see people are starting to use different code from what you've been taught. So it's handy to have this extra documentation as backup so you can go in and check and see what they're trying to say when somebody else writes a piece of code and you're trying to follow it along. So just to recap on terminology, when we say import machine, we're importing a library. I want you to keep in mind a library is just a collection of code. So it's code somebody's written, or you could have written your own library. So import machine is to import a library. When we say machine.pin, the .pin is a class. So it's part of the machine library. It's actually a function within the machine library but when we're looking up official documentation, .pin is a class. So LED underscore onboard has to follow all the same rules that we use when we declare a variable. So it has to start with a letter. It can have numbers and letters in it. Can't have special characters, so we can't use a space in here. That's why we use the underscore, just to give separation between two words to declare our variable. However, when we use a variable to store some information from an API, which is under the machine library or contained in the machine library, we have to use the .value, .on, .off, .toggle, and this is a method. So the .value is a method. So under the talking point selective imports, where it talks about importing part of the machine library, the pin part of the machine library, we do this to optimize our code so that we're not including the entire machine library. We only need a part of it, so that saves space in our memory because we have a limited amount of memory on our Raspberry Pi Pico. And it says here it tells MicroPython to import only the pin function. So the pin function, we happen to know, is a class when we're looking that up in our official documentation. But actually, it's also a function because it's part of the machine library. And keep in mind, a machine library and a function are just code that somebody has previously written for you, or something that you have previously written and are now going to use in this program that you've just written. So the next section in our textbook talks about using the breadboard. If you haven't used a breadboard before, the outer lines are called power buses. We have one in blue and one in red. The one in blue is usually for ground or 0 volts or common on our power supply. The red line is usually for a voltage. Our Raspberry Pi Pico uses 3.3 volts, not the 5 volts we used in digital systems. So it says here all the holes in each rail are connected. Down here it says the 5 holes in each row are connected. So these 5 holes are connected together. They're not connected to the rows on either side. And we also have kind of a trench down the center. I call it the valley. So most of our components straddle the valley. So one leg would go in one side of the valley, the other leg in the other side. Please read this part of the textbook if you're not familiar with using breadboards. So the next step is using an external LED. Now, LEDs don't typically run on the 3.3 volts that our Pico runs on. So we need to install a resistor, and the resistor value that they're going to be using is 330 ohms. So this is a data sheet, and it's for the LTL307P. It's a fairly common red LED. You can see on the diagram here we have the shorter leg is the cathode, meaning the longer leg is the anode, so the longer leg has to be more positive than the shorter leg. So on the data sheet we're going to have some electrical, optical characteristics, and they're telling you this is running at 25 degrees C, so that's pretty normal room temperature. We can see that the forward voltage typically somewhere around 2.1, maxes out at 2.6 volts. So if we were to run this on 3.3 volts, it would burn out. The forward current at 2.1 volts is going to be somewhere around 20 milliamps. So we get these numbers from the data sheet. So I did a few calculations. Remember Ohm's law, V equals IR. So R equals V over I. So the voltage drop across the resistor is equal to the 3.3 volts from the Pico minus the 2 volt drop across the LED. So that leaves us with 1.3 volts. And we divide that by the 20 milliamp requirement of the LED, and we come up with 65 ohms. So why does the book use 330 ohms? If we take Ohm's law and rearrange it so that I equals V over R, then the voltage of 1.3 volts dropped across the resistor, and the resistance 330 ohms gives us 3.9 milliamps. So our LED in our circuit is going to be fairly dim. So if you remember earlier, we downloaded the datasheet for the RP2040. In section 2.19.4, it talks about the pads. And I'm going to come back to this diagram in a minute. But it says here the output drive strength can be set to 2 milliamps, 4 milliamps, 8 milliamps, or 12 milliamps. So I wanted to find out a little bit more about this output drive strength. So in the MicroPython documentation, where they're talking about the class machine pin, they have a section here that says drive specifies the output power of the pin and can be one of pin low power, pin medium power, or pin high power. It says not all ports implement this argument, but it doesn't tell you what the default setting is. So I went out searching on the internet, and I found this little explanation here. It says when the Pi was designed, they used a figure of 3 milliamps per GPIO pin in determining if the regulator could supply enough current. So they're saying 3 milliamp limit was mentioned. So what they're saying is the total current of your Pi is the 17 outputs times the 3 milliamps, so 51 milliamp total current through your Raspberry Pi Pico. However, looking at the schematic, we can see the voltage regulator used. And when we check out the part number in DigiKey, we can see that particular part number is good for 800 milliamps. So it's not a restriction on the voltage regulator. I came across this documentation, which talks about setting the individual drive strength, which differs from low power, medium power, and high power. So I came to the Raspberry Pi forum, and we can see in here they have a discussion about GPIO current ratings. And down here we have a posting by a principal software engineer at Raspberry Pi Limited. And he says, we're having a big discussion internally about this because it's actually not a simple question and definitely not a simple answer. And basically the result is because it's silicon. So I haven't come up with a reason why we're using 330 ohm resistors other than we want to keep the current load on our Raspberry Pi Pico as low as possible. So we have a picture in our book of how they want us to set up this circuit. You'll notice that this is pin 1. So this has to be pin 20. So we need to find out what's coming off of pin 20. So this is 21 through to 40. So this is 39, 38. So they're using 38 coming off and going to this bus. So they're using a black wire going to the ground bus. So I'm thinking this is one of the ground pins on our Pico. So that means they're powering the circuit from pin 20 through the current limiting resistor to the positive of the LED, and out of the negative of the LED we're going to hook it up to the ground bus, and we're going to be using the ground on our Pico. So this is my circuit all wired up to my Pico. You can see my 330 ohm resistor. It's connected to pin 20. And it comes over here and goes to my LED. The other side of my LED comes over and goes to the little black wire that takes me over to the ground bus. So this leg is connected underneath in that set of 5 holes. And the ground bus goes down to this little black wire that comes over here to pin 38 on my Pico. Please note, when I was wiring it up, I did not have it hooked up to my computer. Right? We don't want to hook these things up live, just in case we make a little error. So the legs for the LED, you can see the long leg is lower. So the long leg has to go into the hole for the resistor, and the short leg goes into the upper hole, and it goes to the ground bus. So that would be the correct orientation of your LED. If your LED never turns on, it may be because you've put it in backwards. So you remember I showed you at the back of the book Appendix B, Pinout Guide. And in here we can see that pin number 20 is our general purpose I/O pin 15. So you have to keep that in mind when we define our pin. So it's going to be pin 15. So they're using pin 38 for the ground. Could we have used pin 28 or 33 or 23 or 13 or 3? So you'll remember back to when I downloaded the Raspberry Pi Pico schematic. You can see that pin 3 is connected to pin 8, is connected to pin 13, is connected to pin 18, which goes to our ground or common. And pin 38 is connected to pin 28, is connected to pin 23, which is connected to ground or our common. So yes, we could have used any one of those ground pins. So in Thonny, I've typed in the code as shown in the book. You notice we're going to import the machine library, import the utime library. The variable name, we try to make these as descriptive in our code as possible. So this is going to be the external LED. If I had multiple LEDs, I'd actually put that pin number on here. So I'd say LED external 15. Just so I know when I look at this what pin I'm actually trying to control. I'm going to throw in an endless loop here, and we're going to continuously take our external LED and toggle it. So if it was 1, it's now going to be 0. And I'm going to use a sleep of 1 second. 5 seconds is far too long. So I'm going to go ahead and run this and show you what it looks like. So remember to hook up your USB cable. If you don't, you won't be able to program your Pico. You can see my LED is fairly dim. I've got the lights on right now so that you can see the board and the hookup. And I've got it blinking at about 1 second. So it's toggling on, toggling off, toggling on, toggling off, toggling on, toggling off. So the last section of this chapter is about inputs, reading from a button. So what they're going to have you do is hook up a push button to your circuit board. So what they're going to have you do is basically take off all your components and put in a push button. And then later, on the bottom of page 55, you can see they're going to have you put in the LED and the push button. So I'm just going to add the push button to my circuit and leave the LEDs set up. Now when you take a look at this circuit, you can see that it's a 4-pin push button. So 2 of the pins are connected together, and then the other 2 pins are connected together. So to understand our switch, I'm going to draw it on the screen as a square box, and it has a push button in the center. Now it has 4 leads, so 2 of the leads are on one side of the switch, the other 2 leads are on the other side. So internal to this switch, the leads opposite each other are connected together. So those leads are actually shorted together. The switch part connects across like so. So when you push the button, the switch makes contact. So this lead here is connected straight through your switch. So anything connected in the 5 dots on one side are connected to the 5 dots on the other all the time. It's only when you push the push button down that it's actually connected from this pin here to this pin here. So if we're looking at this circuit from your Pico, they're going from the 3.3 volts to the power bus, from the power bus down to the switch. So this line here is connected through the switch all the time to this set of 5 holes. Now when you press the button, the 3.3 volts connects to this set of holes, which are connected to this pin on the other side all the time. So when you press the button, the 3.3 volts comes through and goes to pin 19 of your Pico. So that gives us our logic 1. When we take our finger off the button, this line is now floating. So typically we would not leave a line floating on an input, so we need to use a pull down or a pull up resistor. In this case, the book likes to use pull down resistors. So I just want to remind you about our digital labs. In lab number 2, where we did basic logic and trainer setup, we used a dip switch and a SIP resistor package in the pull-up configuration. So in lab schematic part E, we had the schematic here. These resistors are pulling the line up. So they're connected to +5. So when the switch is open, the resistor pulls the line up to +5 volts, which gave us logic 1. When the switch is in the down position, it's connected to ground or common. Ground or common, being quite powerful, takes the line voltage all the way down to 0 volts. So you can see in the pull-up configuration, our switch, one side goes to ground, the other side comes along and goes to a resistor, which pulls the line up to +5 volts. So in the pull-down configuration, you can see the switch is connected to +5 volts, which is what we're doing in this case, except we're using 3.3 volts. And on the other side of the switch, we're using a resistor to pull it down to 0 volts. So this is the difference between pull-up resistor and pull-down resistor. So when we look at the data sheet for the Raspberry Pi 2040, I showed you section 2.19.4 about pads, and you can see a pull-up or pull-down can be enabled to set the output signal level when the output driver is disabled. What that means is when we're not using it to power an LED, we're actually using it as an input, we can use the pull-up and pull-down resistors. If you take a look at the diagram in figure 37 here, you can see we have a pull-up, pull-down input, and it goes to some kind of FET, field effect transistor, that's turning on either of these two resistors. So if it turns on the top resistor, it's a pull-up resistor. If it turns on the bottom one, it's a pull-down resistor. These are not resistors in the true sense that you can actually calculate current flow through them, but they do approximate a pull-down or a pull-up resistor going to your pad. So once again, referencing the pinout for the Raspberry Pi Pico, we can see pin 19 is general purpose I/O number 14, and the 3.3 volt output is on pin 36, so it's just 2 below the ground that we used previously. So looking at your push button, you can see the pins are slightly bent. So what you're going to need to do is take your needle nose pliers and straighten out these pins, because if you try and press them in bent into the breadboard, they're just going to bend up underneath the switch and won't make contact. So all I'm going to do is come in with my needle nose and just straighten those pins up. So you want them to be able to push in without bending up underneath the switch. So you want to do the same to the other 2 pins on the other side. So you can see this is my finished circuit. I have the push button installed. So I'm coming off of pin number 36, which is just 2 down from the ground pin. I'm using the red bus to come over to my switch. So the 3.3 volts comes into the switch on this side, and when I press the button, it makes contact to this side and comes over to this blue line that goes back to pin 19, which is general purpose I/O pin 14. So this is the code that they want you to use. You can see we're still importing the machine library. We're still importing uTime. Notice we're going to call our input variable button. And remember, this becomes an object because we're using machine.pin and it's using the API. They're using machine pin 14. Remember, for the LED, we were using pin 15. This time we're calling it machine pin in. And keep in mind, IN is in caps. And then you'll notice that there is a second argument to this statement. So they're saying machine pin and pull down. Please note, pull down is in all caps. So this has turned on the pull down resistor built into the 2040 processor. So when we look at our code, we've got a continuous loop here, and if button dot value, we have to use dot value because button is an object because it uses the API. And remember, when we're testing to see if it's equal, we have to use the equal. If we just use one equal, it would assign 1 into the value, or would try. So here we're saying if the button value, there's the button, so the button value is equal to 1, so that's a logic 1. It's going to print on the screen, you press the button. Then it's going to go to sleep for 2 seconds. Now it's kind of important that you do that. Remember, when you press a button, it's a mechanical switch, and we could end up with some switch bounce. So you probably can't press it fast enough to let your finger off so it doesn't keep repeating. So what we're going to do is, while true, if the button is pressed, you press the button and wait for you to get your finger off that button before it does another check. So I've typed the code into Thonny and I've saved it as button.py. You can see I'm going to import the machine library, import uTime library. The button is going to be equal to GPIO pin 14. It's an input pin, and we're going to turn on the pull down resistors built in. So while it's true, if the button value is equal to 1 or on, it's going to print you press the button and wait 2 seconds before it checks the button again. So I'm going to go ahead and run this. Now you can see it's running down here, but nothing's showing up. So I'm going to press the button, and you can see it says you press the button. So I'm going to press it again, and you can see I can keep pressing it, but it's going to wait the 2 seconds before it accepts the next button press. So moving on to the last section of the chapter, it says inputs and outputs, putting it all together. So now we're going to create code that when we press the button, the LED turns on. So they give us what our finished code should look like. So I'm going to show you what that looks like in Thonny, and then we'll run it. So I've typed the code into Thonny, and you'll see I've renamed it as button_LED. So we're going to import the machine library and the uTime library. We have to define LED external as being on pin 15. The button is going to be on pin 14, and we're going to be using pull down resistors. The code could be a little bit tricky for you to follow, so let me go through it for you. We're going to do an infinite loop. So we're going to continuously just go through the code. So the first thing we're going to do in the code is say if the button value is equal to 1. If it's not equal to 1, we're going to turn the LED off by putting 0 into the value of LED external. So that turns the LED off. If the button is pressed, so if the button's value is equal to 1, we're going to set the value of LED external to 1, so that turns the LED on. Then we're going to put it to sleep for 2 seconds. So the LED remains on for those 2 seconds. When we're done the 2 seconds, we're then going to turn the LED off. And then we're going to come back and restart our loop and check the button value. So if you've now taken your finger off the button, it does an LED external value of 0, turning the LED off. Now the LED was already off, but you're not going to get an error message. So let's run this code and see what it looks like on the actual breadboard. So here's the program running. So you can see right now the LED is not on. And when I press the button, the LED goes on for approximately 2 seconds. So while the code is still running, we can stop it from here. So click on stop, and that will stop your program from running. So in the book it says, congratulations, you've built your first circuit which controls one pin based on the input from another. This is a building block for bigger things. So this concludes Chapter 4. In the next video, Chapter 5, we'll be looking at controlling traffic lights. We'll be using LEDs and the push button, but we'll be monitoring the push button through something called a thread. So our Raspberry Pi Pico actually is a dual core processor. So in this particular chapter, we're going to learn how to do a second thread or use the second core at the same time the first core is running. So we'll be able to check to see if the push button is pressed while the LEDs are going through a light sequence. So please don't forget to subscribe, and we'll see you in the next video.